This is SpaceTime, Series 20, Episode 24. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, the Peter Pan galaxies that seem to never grow old, a new portal to unveil the dark sector of the universe, and were Martian volcanoes still active when Earth's dinosaurs, other than birds, went extinct? All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new survey has doubled the number of Peter Pan galaxies known to exist. Peter Pan galaxies are young, compact radio galaxies, which produce powerful jets of radio energy shooting out from their galactic cores like lighthouse beacons. The radio jets are generated by supermassive black holes, feeding on stars, planets, gas, or anything else that just happens to get too close. The new study reported in the Astrophysical Journal will help astronomers try to work out why these specific galaxies never seem to age as they evolve, and consequently why there are so many more young radio galaxies than old ones. For a long time, astronomers thought all small galaxies would eventually evolve into massive ones. After all, it's how the Milky Way and Andromeda grew, and it's how most of the galaxies we see around us grow and evolve. However, this new study has found far too many small galaxies relative to the larger ones, and that suggests that some, like Peter Pan, never mature into adults. In a survey of some 90,000 radio galaxies, astronomers were able to identify 1,500 compact galaxies among them. These compact Peter Pan galaxies were considered extremely rare, but the discovery of so many of them will allow astronomers to begin studying their properties in detail. As the name suggests, all radio galaxies shine brightly at radio wavelengths, and most if not all galaxies are thought to have supermassive black holes at their centres. Now, a supermassive black hole, typically with masses of millions to billions of times that of our Sun, powers this outpouring of radio energy. You see, as stars, planets, or clouds of gas and dust fall into black holes, they release vast amounts of energy and matter before disappearing beyond the black hole's event horizon, the physical point of no return, beyond which matter, which is being crushed, ripped, and stretched apart at the subatomic level, falls forever into the black hole's singularity, the place where science's understanding of physics breaks down. All this energy and matter released before an object passes beyond the black hole's event horizon can get focused by the black hole's magnetic field lines into two jets, travelling in opposite directions at nearly the speed of light. As these jets blast through the galaxy, each generates its own lobe or hotspot of radiation as it interacts with interstellar gas in the galaxy. Now, according to one model, compact radio sources are young because the jets haven't yet had the time to reach far beyond the central black hole. And so the hotspots are still relatively close together, and we see them as compact sources. Over time, these jets reach further and further out into the galaxy and even beyond the galaxy itself. Consequently, these hotspots are further and further from each other, and instead we begin to see them as a more extended double-lobed source. In this simple model, the overabundance of young compact radio galaxies raises the question, why don't we see young compact galaxies mature into older, more extended radio galaxies? However, another model hypothesizes that the relationship between the age and the observed size of a radio galaxy isn't quite so straightforward. That's because a compact source could well be compact not because it's young, but because the gas and dust within the galaxy is really dense, so thick it actually prevents the jets from extending far from the central black hole. And as a result, these galaxies remain compact despite their age. Now, if correct, it means the environment around the central region of the galaxy can hinder and even stop the growth of a radio galaxy's AGN, or active galactic nuclei. The authors made the discovery using data gathered by the Murchison Wide Field Array Interferometer Radio Telescope in the Western Australian outback. The discovery was possible because, unlike conventional radio telescopes, which observe tiny patches of the sky at one time, the Murchison Wide Field Array sweeps huge areas of the sky at once. and is also capable of observing across a far broader range of wavelengths. The array combines signals from over 2,000 separate antennas. With an area of some 2,000 square metres, it has a collecting area equivalent to a conventional radio telescope dish. The array is located at the Murchison Radio Astronomy Observatory, which is also the site for the Square Kilometre Array project, located some 700 kilometres north of Perth. Over the past 3 years, it's been used to survey some 90% of the southern sky, as part of the Galactic and Extragalactic All-Sky Murchison Wide Field Array, or GLEAN survey, which is looking at some 300,000 galaxies. One of the study's authors, Jack Lyon from the University of Melbourne, says the new tally will help astronomers better understand the relationship between the size of these radio sources and their age, as well as the nature of the galaxies themselves.
The crux of this sort of research that we've been doing is looking at how large they get and how their evolution occurs. So you can have these massive radio galaxies which cover huge areas of the sky if they're close enough, but you can't see them obviously because they're in radio waves, so you can't see them with your eyes. But what this team's been trying to do is work out why there are so many small ones, because these radio lobes, the jets that shoot out from this black hole, they travel into the local environment that the galaxy lives in. The time-tested model of these galaxies as they evolve is they kind of blow these bubbles in the surrounding area. They blow out these jets, and they should just get bigger and bigger with time. But this research has been looking at the compact ones, the ones that don't grow with time, and trying to work out why there are so many of these smaller ones compared to the large ones. If evolutionary model was correct, we should see sort of a normal kind of aging in the population, sort of a comparison between those big and small ones. But the compact ones seem to be more prevalent.
When I think about things like that, my immediate response is, well, central black holes have simply run out of food so that they can't keep extending further out. But it takes time for the radio beam, the lobe, to fade away.
Yeah, so it is incredibly dependent, obviously, on what these radio galaxies produce, dependent on what's sort of surrounding them, you're right. So dependent on how much fuel they have is how long they can live. But given what we know about the sort of the surrounding matter, the amount of gas and dust that should be around these types of galaxies, the fact that we don't see as many large ones, that's not enough to account for why we don't see that many large ones. There are things that kind of indicate what you're talking about. There are restarted double lobe radio galaxies, which are very cool, which are possibly caused by sort of reinvigorating this AGN, so the active galactic nuclei at the center, as you say, need fuel. It needs this gas and dust to fall onto it.
You got to eat.
Yeah, you've got to eat, exactly. But it's possible that they go on a diet for a bit of time and then get to eat again. So they run out of fuel, like you say, so they can't produce these huge energetic jets. But then possibly the galaxy that they live within interacts with another galaxy, strips off some more gas from it, and then can restart again. And so you get these kind of double jets where you have one that's further away, big and sort of diffuse as it spreads out into the surrounding medium, and then another one that catches up with it. But I think, as we were saying, that's not quite enough to explain why we see so many of these compact ones compared to the huge radio galaxies.
What are the main models to try and describe these? The evolutionary model, which is, I guess, what you guys are really looking at.
Yeah, so the older models sort of say that, okay, all your matter, as it falls on, it gets shot into these big radio lobes. They get pushed at relativistic speed away from the core, and as they get pushed into surrounding areas, the matter, the plasma inside, cools, and you can sort of tell how old this galaxy is by the spectral behavior of the emission. So if you look at the power that's emitted at different frequencies, the shape of that spectrum changes with time as the electrons in that plasma lose energy. So the idea was that as these galaxies sort of get bigger and bigger, these lobes get larger and larger, the spectrum slowly flattens because it's losing energy. And the whole sort of way of looking at the evolution was there's an event where you start these radio jets, and like you say, after some time, that runs out of fuel, and these things just keep getting bigger and bigger as they push out, and their spectrums get flatter and flatter. You don't see so many of these huge radio galaxies. You see quite a lot of these compact ones. And with the advent of these new low radio frequency telescopes that are now dotted around the world. The one that was used for this research is the Murchison Wide Field Array in Western Australia. But there's also Northern Hemisphere compatriots such as LOFAR telescope in India, which is called the GMRT. They're able to make these new observations at these low frequencies that give us lots and lots of data points. We're able to get large amounts of frequency data, which lets us far better model the spectral behavior. So by fitting different models, you can kind of model how these electrons are losing their energy, what contributions or what physical processes are causing these spectra. And the main outcome of this paper was that it looks like a lot of these compact sources are actually just surrounded by more gas or dust or sort of a certain environment that actually frustrates the lobes, so it stops them from being able to push out into the surrounding medium. They actually kind of get stuck. So they may have actually similar ages, or they're getting to a certain age, but they're not spreading out because they can't actually push into the surrounding medium.
There's a physical barrier there of gas and dust that's preventing them from expanding beyond the compact young stage, or the compact stage at least.
The compact stage,
Yes.
they're not actually able to push out and get large.
What's the difference between a radio galaxy like the ones we're talking about here and blazars and quasars, apart from the fact that blazars and quasars are a lot further away in the distant universe? Or are they just the same thing?
The argument of blazars and quasars is that they're the same thing but seen from different angles. And there is still quite a lot of contention in the field about whether they are physically different things or whether they're just the same thing seen from different angles. I mean, the basics of all of these objects is exactly the same. It's just you have some kind of black hole and you have some matter falling onto it. No one really knows exactly if they accrete matter in different ways or whether it's just an observational difference. That's still kind of the question that's being asked. People are actually trying to get more and more sophisticated models these days to actually try and see if there's a physical mechanism difference or whether it's actually just the projection effect, like you say.
Okay.
It's incredibly difficult to model these things because the resolution in the spectral observation that you need to be able to tell the difference between sort of the areas close to where this black hole is operating and the areas far away is incredibly exquisite. So you need extremely good observations and you also need very good theoretical models. People are still working on it. They're not quite there yet.
That's Jack Line from the University of Melbourne. You're listening to Space Time. I'm Stuart Gary. Scientists are developing a new portal to unveil a mysterious dark sector of the universe. Once upon a time, 13.8 billion years ago to be exact, the universe was nothing more than a hot soup of particles known as a quark-gluon plasma. In those ancient days, together with visible particles, other so-called dark particles may also have formed. Billions of years later, scientists have catalogued 17 different types of elemental visible particles. Particles which simply cannot be broken down into anything smaller than themselves, other than possibly strings of energy, depending on which cosmological model you prefer. The most recently discovered of these 17 visible particles is the Higgs boson. And together they all create what we call the standard model of particle physics, the basic foundation stone of science. The problem is, the standard model isn't complete. There are bits that aren't accounted for, like dark energy and dark matter. So, scientists are still struggling to detect other hidden particles beyond the standard model, particles that constitute the dark sector of the universe. Now researchers from Korea's Institute for Basic Science have proposed a new hypothetical portal connecting two possible dark sector particles. The new hypothesis, reported in the journal Physical Review Letters, could open a new perspective into the murky understanding of the dark sector, which would have huge implications for cosmology and astroparticle physics. Physicists already have plenty of ideas about what these dark sector particles could be. One candidate's the axion, a hypothetical elementary particle first postulated in 1977 to resolve the strong charge parity problem in quantum chromodynamics. If axions exist that have extremely low masses, no electrical charge, and zero integer spin. You can sort of think of integer spin as being a little bit like, but really not, angular momentum. In particle physics, the strong charge parity problem is the puzzling question of why quantum chromodynamics doesn't seem to break charge parity symmetry. According to charge parity symmetry, the laws of physics should be exactly the same if a particle is interchanged with its antimatter counterpart while its spatial coordinates are inverted. The problem is, a violation of charge parity symmetry was discovered in 1964 with the decay of neutral kaons, bound states of strange quarks or antiquarks with an up or down antiquark or quark. Quarks are elemental subatomic particles that come in 6 types: up, down, charm, strange, top and bottom. Each has a different mass. All quarks have half-integer spin. Up, charm and top quarks have 2/3 charge, while down, strange and bottom quarks have 1/3 negative charge. Quarks also come in 3 so-called colours, usually commonly referred to simply as red, green or blue. And just to further add to the complications, bottom quarks are sometimes also called beauty quarks. Charge parity symmetry plays an important role in attempts of cosmology to explain the dominance of matter over antimatter. You see, equal amounts of matter and antimatter would have been created in the Big Bang 13.8 billion years ago. The problem is when matter and antimatter meet, they annihilate each other. So the universe should have been destroyed as soon as it began, and clearly that didn't happen. According to quantum chromodynamics, or QCD, that's the theory of the interactions of the strong nuclear force, there could be a violation of charge parity symmetry in strong nuclear force interactions. The strong nuclear force is one of the four fundamental forces of nature, together with the weak nuclear force, gravity, and the electromagnetic force. The strong force is the fundamental force holding ordinary matter together, because it confines quarks into larger subatomic particles, such as light matter-antimatter particles called pions, and of course the protons and neutrons often found in the nucleus of atoms. Gluons are the carriers of the strong nuclear force, in the same way as photons carry the electromagnetic force in quantum electrodynamics. Now, if axions really do exist, and if they have a low enough mass within a specific range, then they could be a component of cold dark matter, a mysterious substance which makes up some 80% of all the matter in the universe, but which seems to be invisible and only seems to interact with normal matter gravitationally. The other candidate scientists are looking at is known as a dark photon. Again, it's a hypothetical elementary particle, proposed as an electromagnetic so-called dark force carrier for dark matter and other dark sector particles. Dark photons would theoretically be detectable by mixing with ordinary photons and their subsequent effect on the interactions of known particles. Physicists believe that the dark sector communicates with the standard model of particle physics through portals. For example, a vector portal would allow the mixing between dark photons and photons, and an axion portal would connect axions to photons. There are several possible portals which physicists have identified, and each portal is a major tool in theoretical and experimental studies searching for dark sector particles. The authors of our paper have hypothesized the existence of one of these portals, which they've named the dark axion portal. It should connect dark photons and axions. The central idea of the dark axion portal is based on the observation that heavy quarks could also have a dark charge that couples to the dark photon. So, through heavy quarks, such as the charm and bottom quarks, axions, photons, and dark photons could possibly interact with each other. The authors think that if the dark axion portal really does exist, it could spring forth new ideas for new experiments. So far, the axion search has been performed using only the axion portal, which theoretically should connect the axion to a pair of photons through a process called axion-photon-photon coupling. Similarly, the dark photon search has been performed using a different portal known as a vector portal, which theoretically should allow a small mixing between dark photons and regular photons. If it exists, the dark axion portal could link the two, and thus provide a meaningful connection between standard and dark physics. I'm Stuart Gary. This is SpaceTime. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and junk on the web I find interesting, important, or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter. And on Facebook, just go to www.facebook.com/spacetime with Stuart Gary. There's growing evidence that far from being a cold, dead world, Mars may still have been geologically alive until very recently. The new findings, reported in the journal Earth and Planetary Science Letters, indicate volcanoes were still erupting on the red planet's surface as recently as 50 million years ago, which in geological terms is just yesterday. The findings are based on new NASA research showing that the giant Martian shield volcano Arsia Mons produced one new lava flow at its summit every 1 to 3 million years during its final peak of activity. This study implies that the last volcanic activity there ceased about 50 million years ago. That's not long after the Cretaceous Tertiary mass extinction event, which wiped out some 70% of all life on Earth, including all the dinosaurs other than birds. Located just south of the Martian equator, Arsia Mons is the southernmost member of a trio of broad, gently sloping shield volcanoes, collectively known as Tharsis Montes. We know Arsia Mons was built up over billions of years, although the exact details of its life cycle are still being worked out. The most recent volcanic activity is thought to have taken place in the caldera, the bowl-shaped depression at the top where 29 volcanic vents have been identified. Until now, it's been difficult to make precise estimates of exactly when this volcanic field was active. One of the study's authors, Jacob Richardson from NASA's Goddard Space Flight Center in Greenbelt, Maryland, estimates the peak activity for the volcanic field at the summit of Orissa Mons probably occurred around 150 million years ago, a time which equates to the late Jurassic period here on Earth. He says the volcanic activity at the site probably died out around the same time as Earth's dinosaurs, other than birds. However, he speculates that it's possible that the last volcanic vent or two may still have been active within the last 50 million years. The massive caldera of Orissa Mons is over 110 kilometres wide. The authors used high-resolution cameras aboard NASA's Mars Reconnaissance Orbiter to undertake a detailed examination of volcanic features within the caldera. They mapped the boundaries of the lava flows from each of the 29 volcanic vents. This allowed them to determine the stratigraphy or layering of the flows. The authors also performed a technique called crater counting, which tallies up the number of craters at least 100 metres or more in diameter in order to estimate the ages of the flows. Using a new computer model developed by Richardson and colleagues from the University of South Florida, the two types of data were combined to determine the volcanic equivalent of a batting lineup for Orissa Mons' 29 vents. The authors found that the oldest flows date back around 200 million years. But the youngest flows probably only occurred between 10 and 90 million years ago, with the most likely being closer to 50 million years ago. The modelling also yielded estimates for the volume of flux for each lava flow. At their peak about 150 million years ago, the vents in the Orissa Mons caldera probably collectively produced about 1 to 8 cubic kilometres of magma every million years, slowly but surely adding to the volcano's size. Richardson describes it as a slow, leaky faucet of magma. Orissa Mons was creating about one volcanic vent every 1 to 3 million years at its peak, compared to one every 10,000 years or so in similar regions here on Earth. A better understanding of when volcanic activity on Mars took place is important because it helps scientists better understand the red planet's history and internal structure. A major goal for the Mars volcanology community is to understand the anatomy and life cycle of the planet's volcanoes. You see, Martian volcanoes show evidence for activity over a far larger time span than those on Earth. The new study gives scientists another clue about how activity at Orissa Mons tailed off and how the huge volcano became quiet. Volcanism is one of the principal methods a planet uses to release heat from its interior. Unlike the Earth, which also vents internal heat through tectonic plate activity, the Martian crust is thought to be generally too thick for extensive global plate tectonics to have evolved. However, tectonic boundaries have been discovered on Mars. The massive Valles Marineris Canyon, a huge tear ripped across a third of the red planet's surface, is believed to be evidence of a horizontal sliding tectonic boundary dividing two major partial or complete Martian plates. The recent findings suggest Mars has been geologically active within the last few million years and possibly may still be active today. However, the red planet's smaller size, it's just a third that of the Earth, has allowed Mars to cool down internally much faster than the Earth. Martian volcanic features range in age from the Nocean epoch more than 3.7 billion years ago to the late Amazonian epoch, which is less than 500 million years old. It shows that Mars has been volcanically active pretty well throughout its history. Mind you, scientists have never recorded an active volcanic eruption on the Martian surface. Searches for thermal signatures and surface changes within the last decade or so have also failed to yield any positive evidence of current active volcanism on the red planet. However, the European Space Agency's Mars Express orbiter has imaged lava flows which were interpreted in 2004 as having occurred within the past 2 million years, and that suggests extremely recent geological activity. An updated study in 2011 also estimated some of the youngest lava flows on the red planet probably occurred in the last few tens of millions of years. The young age of all these discoveries make it highly possible that Mars isn't yet quite volcanically extinct. This is SpaceTime. I'm Stuart Gary. China has successfully launched a new rocket. The Katusha-2 blasted off just after sunrise from the Jiaquan Satellite Launch Center in the Gobi Desert region of Inner Mongolia. The three-stage solid-fueled rocket is based on Beijing's existing Dongfeng 31 intercontinental ballistic missile, with its standard 1 megaton thermonuclear warhead replaced with a satellite payload. The former ICBM is thus capable of carrying payloads of up to 800 kilograms into low Earth orbit. The launch, which was China's third for the year, delivered the experimental Tianqing-1 spacecraft into an elliptical sun-synchronous orbit. Tianqing-1 is a remote sensing and telecommunications satellite. It features a new technology demonstrator small satellite bus design. Beijing's next launch, which is scheduled for any day now, will see a Long March 2D rocket carrying 2 telecommunications satellites. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more space time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and junk on the web I find interesting, important or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter. And on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts or Audio Boom. This has been another quality podcast production from Bytes.com.